Before we can look at spectra, we have to first understand what electromagnetic radiation is. Here you see the electromagnetic spectrum, which includes all types of electromagnetic radiation. These different types of radiation are all essentially the same as each other and differ only in terms of their wavelength and frequency. In order of increasing frequency, it includes radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, and finally gamma rays. Each type of radiation has unique properties and applications, from radio communication and medical imaging to UV sterilization and gamma ray astronomy. The visible light portion is the only part detectable by the human eye, which has evolved to be able to see these frequencies. Other frequencies require specialized instruments to observe. Like all waves, electromagnetic waves have three properties: wavelength, frequency, and speed. All electromagnetic waves, however, travel at the same speed, the speed of light. So we will only consider wavelength and frequency, since only these two variables change for electromagnetic waves. If we stop this wave moving for a moment, we can measure its wavelength, the distance between 2 points with the same amplitude. For example, the distance between 2 peaks or 2 troughs. Since it's a distance, wavelength is measured in meters. Frequency is the number of waves that pass a given point per second and is measured in hertz. Here you can see that if we increase the frequency of the wave, it will look like this, and you can see that there are more waves passing our point in space per second, in other words, a higher frequency. A wave with a high frequency transfers a lot of energy. If you can imagine yourself standing in the sea being hit by waves this often, you would get a sense of the greater amount of energy being transferred by our high frequency wave. We can stop the wave for a moment and record the wavelength of this high frequency wave, and you can see that it is quite short. We can summarize the relationship then between these variables by saying that a high-frequency wave has high energy and short wavelength. If we lower the frequency of the wave, it will look like this, now with less waves passing that same point in space per second. Again, we can stop the wave and measure the wavelength, and you can see that this low-frequency wave has quite a long wavelength. In the same way as before, low-frequency waves will transfer less energy than high-frequency waves. We can summarize the relationship between these variables then by saying that a low-frequency wave has low energy and a long wavelength. We can summarize the important relationship between energy, wavelength, and frequency. The energy being transferred by a wave will be proportional to the frequency of the wave and inversely proportional to the wavelength of the wave. We have a special equation that relates these variables. Since E is proportional to frequency, if we introduce a constant, we can let them be equal to each other. This constant is known as Planck's constant, and it gives us what's called Planck's equation, which we'll see more about later. If we now return to our electromagnetic spectrum again, we can see how the relationship between frequency and wavelength changes across the spectrum. The two vary inversely with each other. Starting from the left, radio waves have a very long wavelength and a very low frequency, and are therefore low energy waves, just as well since they are everywhere and passing through your body every moment. Moving up through the spectrum, we come to microwaves, which have a shorter wavelength and a higher frequency, and therefore transfer more energy. Next, we have infrared waves, again with a higher frequency and a shorter wavelength. After that, we have visible light, the region of the electromagnetic spectrum that our eyes have evolved to recognize. Beyond the visible spectrum, we have ultraviolet light, a shorter wavelength and a higher frequency than visible light. Ultraviolet light then transfers more energy, and we are now starting to deal with waves that are transferring enough energy to be dangerous. This is reflected in the fact that ultraviolet light can cause sunburn. X-rays have a higher frequency and a shorter wavelength again and transfer even more energy. There are strict limits, therefore, on how much X-ray exposure a person can have per year, and pregnant women are advised to avoid X-rays. Finally, we have extremely high frequency and high energy gamma rays. Even small exposure to gamma rays can be dangerous, leading to the development of various types of cancer. It is worth taking a closer look at the portion of the electromagnetic spectrum known as visible light. Here we see all the colors of the rainbow, ranging from red at the infrared end to violet at the ultraviolet end. Again, you can see the same trend as we move from red towards violet. The wavelength is decreasing, but the frequency is increasing, as they vary inversely with each other. Understanding this pattern in wavelengths and frequency is key to understanding the nature of light giving off by atoms, as we shall see in another video. For now though, let's take a closer look at the different types of spectra. It was the brilliant Danish physicist Niels Bohr who would use spectra to build what became known as the planetary model of the atom, where he imagined electrons orbiting the nucleus in much the same way as planets orbit the sun. If we pass white light through a prism or diffraction grating, or indeed a raindrop, it breaks up into its constituent colors of different frequencies, red at the low frequency end and violet at the high frequency end. This spread of colors is known as a continuous spectrum, as no frequency is missing between the red and violet ends. The different colors blend into one another smoothly, without any interruptions or gaps. This range of frequencies is known as visible light, simply because it is the range of frequencies that our eyes have evolved to be able to see. As we said before, beyond the colors at either end, invisible to our eyes, you have infrared at the red end and ultraviolet at the violet end. Energy transferred by visible light fuels all life on our planet, but of course all forms of electromagnetic radiation transfer energy, since of course they're waves. If we put a thermometer beyond the red end of the spectrum, you will see the temperature increase quickly. The point is that light can transfer energy, and as we shall see, this energy can be absorbed by and cause changes to atoms. It was known before Niels Bohr came along that if you take gases and put them in a discharge tube, a glass tube where they are at low pressure and can have electricity pass through them, the light that comes off them is different. In the case of hydrogen, for example, the light is a reddish pink. When this light is passed through a prism, we now see four distinct colored lines, as opposed to the continuous spectrum we saw before. This is known as an emission line spectrum, or simply an emission spectrum, as this light is being emitted by the hydrogen itself when it is excited by the electricity in the discharge tube. An emission spectrum can be recognized because it always has colored lines on a black background. Note that the locations of these colored lines on the emission spectrum are the same as in the continuous spectrum. It is just that the light from hydrogen is missing the vast majority of frequencies that are in white light and contains only the four specific frequencies or colors that we see here. Note also that in the same way that the prism split white light before into all its component frequencies and colors, the prism now is splitting the light that is coming off the hydrogen into its component frequencies. If you combine these four colored lines in the same way that you might mix paint, you get the same reddish pink color that your eyes see when you look at the hydrogen discharge tube. Our eyes are just incapable of seeing the constituent colors in the mix that give hydrogen its characteristic pink glow in a discharge tube. We need a prism to break it up into its constituent frequencies. When we look at the light from other elements in discharge tubes in the same way, we see different arrays of colored lines. Indeed, every element has its own unique emission line spectrum, and this can be used to identify the element. The element helium, for example, which is rare on Earth, was first identified by noting that the light coming from the sun had lines with a collection of frequencies that no other known element had, so it had to be a new element. It was named accordingly. Helium comes from the Greek helios, meaning the sun. We can identify elements by exciting the atoms in other ways too, not just using electricity. Using the heat from a Bunsen flame, for example, and holding a salt in the flame will color the flame distinctively so that we can identify the metal in the salt. This, of course, is known as a flame test, and the principle is the same as we saw in the discharge tube. If we pass this light through a prism, we would see again the constituent frequencies in the light being given off by the atoms. If we return to our hydrogen emission spectrum, we see something very interesting. We can see here that as we move from right to left, our frequency is increasing since we are moving from the red towards the violet end. We also notice that as we move in this direction, the lines are becoming closer together. We say that they are converging at higher frequencies. We could of course also say that they are converging at longer wavelengths, and it would mean the same thing. This is the key feature that you should remember for the hydrogen emission spectrum, and we will see what this is when we take a closer look at the arrangement of electron shells in atoms. But for now, remember that in a hydrogen emission spectrum, we always see lines becoming closer together as we move towards the higher frequency end of the spectrum. There is also another type of spectra known as absorption spectra that we should consider. In emission spectra, we are exciting the electrons in atoms, either with electricity in a discharge tube or heat from a Bunsen flame, and we then pass the light given off through a prism to see the constituent frequencies. It is also possible, however, to excite the electrons in atoms using light. Consider the scenario where white light enters a sample of cold hydrogen gas. In this situation, the hydrogen atoms will absorb specific frequencies of light and re-emit these same frequencies of light in all directions, such that if we examine what is left of the white light that has passed through the sample and then through a prism, we see something very interesting. We now see a continuous spectrum that is missing the specific frequencies that were absorbed. This is what is called an absorption spectrum. An absorption spectrum is recognizable as black lines on a colored background, the reverse of the emission spectrum. Note that the locations of the black lines correspond exactly with the locations of the colored lines on the emission spectrum, since of course, in the exact same way, these frequencies were emitted by the hydrogen atoms. But now we are looking at what remains of the white light emerging from the sample minus these frequencies. Absorption spectrometry is incredibly useful in astronomy as it allows us to look at light coming from distant stars and planets and tell what elements these atmospheres are composed of based on which frequencies are missing from the light. Questions on spectra in paper 1 of the IB exam very often focus on the hydrogen emission and absorption spectra. Here in this typical question, we are asked to identify the key features of a hydrogen emission spectrum. Answer A refers, of course, to a continuous spectrum. Answer B is a nonsensical answer. Answer D is not true, of course, as lines are never evenly spaced. Rather, the answer is C. Lines become closer or converge at higher frequencies. In this question, we are presented with a sample emission spectrum for hydrogen, and we are asked to compare properties of lines on the spectrum. Here we need to be clear on the relationship between wavelength and frequency. We can see straight away that since the lines are converging as we move to the right, that this means that frequency and energy are increasing as we move to the right, and wavelength is decreasing. Answers A, B, and D are therefore incorrect, while C is true, since D is to the right of A, and so has a higher frequency, and therefore a higher energy than line A. In this question, we are asked to identify which emission spectrum shows lines converging at higher frequencies. Straight away we can rule out A and B, as neither of these spectra show convergence. We are told that moving to the right, the wavelength is decreasing, which of course means that the frequency is increasing as we move to the right. We are therefore looking for convergence on the right side of the spectrum, which of course means D is the correct answer. Stay tuned to see the next video on spectra, where we will look at how electron arrangements in atoms explain these patterns of lines that we see in emission and absorption spectra. If you'd like to see more of this content specifically designed for IB chemistry, please consider liking and subscribing, and make sure to click the bell icon so you never miss a new video. Thanks for watching.